Hi everyone, I thought it was about time that the split half package got a little video tutorial just to give some people some ideas about how it works, how we can play with it a little bit to make it adaptable to the circumstance that you need it for. And yeah, just have a play, see how it works. I'll be using data from Hedge and colleagues, an awesome paper that I'll also add a link to in the description. It's a paper that everybody should read, it's awesome. I'll give a basic overview of the main functionality within split half and just run our way through it. I'll live code it, which is also going to be fun and games because my spelling is awful. So be kind. I'm happy to. I'll make the comments open. My email's probably somewhere. If anybody has any questions about any parts of it, I won't have time to cover quite everything, but hopefully it'll be enough to kind of get people started and firing in. Over time, I've had a good few emails about how to do different things within the package. In the last maybe year or so, there's also been a few kind of bigger changes that may have changed some of the advice that I've given over time. So I thought it'd be kind of a good point to sort of timestamp things a little bit and make a quick video. Okay, so let's dive in. So, as I said, we'll be looking at the hedge data. I've already done some processing on it just to make sure that we're not spending half the video just me going through how the data was processed. I've done things like already removing outliers, removing the practice trials, stuff like that. Nothing massively important for our purposes, but just good to know. Okay, I'll play with the windows a bit as we go so that we can see more things. So let's rerun that just so we have a nice table. So I've also selected pretty much only the variables that are of interest to us right now. So we could decide to make things, to organize things by block. We won't. We actually don't need to know the trial number in split half. It'll automatically just add a column to be able to do all that. But at the same time, I thought it'd be worth just leaving it in for now. If anything, to make it clear that, so the fourth trial here, the seventh trial must have been removed for being incorrect, that kind of thing. So just to also demonstrate that the thing's been removed. Arrow direction and condition refer to the conditions that's in. We only need condition in this case. It's a bit of a shame that it's called condition because I use that terminology later on as well, but I'll try and make that clear throughout. In this case, it refers to the trial type or the trial condition. So this is from a Stroop task. So in this case, the congruent is if the wording matches the color, and incongruent is if the word does not match the color. Or the equivalent for any number of tasks where you have an incongruent and an incongruent condition in which the outcome measure of interest is the difference between the average response times, in this case, between conditions. You'll see that the corrects are all 1 here because I've already removed error trials. It's really important before you run really anything on reliability estimates to have already done the processing of the data beforehand, or at least make sure that any processing done is matched with the processing that will be done in the final kind of analysis. So if I were to remove all reaction times under a certain amount for the reliability but not for the main analysis, we're actually calculating reliability not for the thing that we analyzed, as a basic example. Okay, reaction time here is in milliseconds, PPID is the participant ID, and time is going to be 1 or 2, and that refers to the time point within the data. So Hedge and colleagues collect data at 2 time points, I think 2 to 4 weeks apart. So we'll separate that by time point within what we do today as well. Okay, now that we know what the data looks like, let's load our packages. In this case, I think all that we'll actually need is the split half package. if I called it splithalf rather than spithalf, that would be good. Now, it's already loaded. Normally you would get a message that gives the version number and so on. I loaded it as practice thing, so it's not here now, but that's fine. So the main kind of workhorse of the splithalf package is the function splithalf, unsurprisingly. Now, I developed splithalf mainly to work with more behavioral measures, so things like the stroop task, the flanker task, the .probe task, all of these tasks that require a difference score usually as the main outcome of interest, and sort of traditional approaches to reliability like convex alpha and so on aren't really doable. Ideally, we'd have some test-retest evidence, but in an awful lot of cases in these studies, you only have one time point, so I kind of consider it that internal consistency is probably the best that we can do sometimes in terms of looking at reliability, even if it's far from an ideal way of looking at reliability, or even sometimes internal consistency. Anyway, so the first thing that we'll throw into splithalf is the data that we're interested in, which is our hedge raw. Splithalf has plenty of arguments. An awful lot of them that we'll end up putting in relate to just the naming of the variables within the data set. So if the variables are named the same as in the defaults, it's fine. We don't have to worry about it. But it's most of the stuff that goes in is actually just the practical stuff like that, rather than the main decisions that we'll be making. Okay. Now we're interested in response times rather than accuracy in this case, or signal detection type indices. So we'll specify that as outcome. So outcome is equal to RT, means that we're looking at the response times. If it's set to ACC, we'd be interested in accuracy. I could demo that as well, but as I've already removed inaccurate trials, we're not going to have any variants to actually run this, so it's not going to work. But the inputs are essentially the same, with the difference that you'll actually have to include var.acc. But I'll explain that later as well. Now the main score of interest in this case is a difference score. So that is the outcome measure that we're interested in, is the difference between the average response time in the congruent to the average response time in the incongruent condition. We could also take average, so score equals average, and that would just give us a kind of average across the response times. We could separate that out into congruent or incongruent trials as well to give us the reliability of that. Typically, that's going to be very high. It seems to be the difference score, and mathematically, it will be the difference score that will be lower reliability. It tends to be, in my experience, when I've looked at other people's data, that looking at the reliability of just an average response time is usually very high, which makes sense, I think. We can also specify difference of difference with underscores in that. This is also in all the documentation, so it's not hugely important right now. And that will take the outcome measure of interest as the difference over time, essentially. So, or the difference over time between the difference scores. So, for example, if we were interested in correlating the difference between time 1 and time 2 on the Stroop score with some other variable, I don't think that's going to be done too often, but I coded it up just out of interest, really, quite early on. Okay, so the other thing that we'll specify that's a bit more specific to the package is permutations. And permutations is the number of random splits that the function will run in order to estimate reliability. So the actual process that the package takes is to split the data however many times we specify here, just randomly in half. It will calculate the summary like the final stats for each of the scores, so the individual's different score, for example, separately for each of those halves, and correlate them for each split. And the average Spearman Brown corrected correlation is our reliability estimate. This also allows us to plot a distribution and to consider this as a distribution of reliability estimates, which I think offers us something kind of nice over a point estimate. And I'll get onto that a little bit more later as well. Okay. So because we're looking at a difference score, we need to specify what we're actually calculating the difference in. So first we'll specify var.compare. So this is going to be our variable that that corresponds to the different kinds of trials. One of the things that I tend to often do in the console, just to make things easier for myself, is to not unique. That's silly sound. Is to run call names with data set. This is purely because I forget often whether there's capitals, whether there's different spellings, and all of that kind of stuff. It's always helpful for me as a reference. So in this case, and perhaps confusingly, the condition within the data refers to the trial type. So var compared, in this case, is condition. And we're interested in comparing the congruent condition, and we'll specify that as compare 1, and compare 2 as the incongruent condition. Now, just to double check that, there's better ways of doing this. But just so that I can double check my spelling, yep, there's no capitals. Awesome. So this now tells splithalf that we want to compare the average response time in the congruent versus the incongruent condition, and that's important. So currently, if we were to run this as it is, we'd be collapsing over time, which might not be ideal. We probably want to consider the different time points as being separate, so we'll specify that next. Now, in this case, where the confusion comes in is I've called things like that condition within the code. So in this case, var.condition is going to refer to time. Oh. Now, in this case, var.condition could be any kind of grouping variable. There might be different emotion conditions. There might be different experimental conditions, for example, within tasks that we want to estimate different reliability estimates for. Again, the main thing is that whatever we specify here corresponds to how the data is actually analyzed. Now, specifying the var.condition isn't quite enough. We also need to specify the actual list of conditions that we're interested in. Now, this is purely because I'm well aware that depending on the data that people have, they might not want to look at every condition at once. They might want to look separately by block, for example, and it can be a lot easier to specify the specific blocks of trials or the specific conditions that people are interested in. As we saw earlier, there are 2 time points, so we'll put that in a list with the C to give us our 1 and 2. Now, splithalf is almost there. What it still doesn't know is how we're specifying by participant. So, one of the really helpful things in the newer versions of RStudio, it wasn't like this when I started, I love RStudio so much, is popping up with these suggestions. They tend to come up pretty quickly for this, and it's just useful. I find myself using that more than anything else because I forget what's going to go into there quite often. So in this case, we called our participant variable participant ID, and we're also missing telling splithalf what our response time variable actually is. So we'll plug that in just now as well. Okay, reaction time there. Now this looks like everything. I set the permutations to 5,000. This is kind of my own default. I think realistically anything above 2 or 3,000 is going to be fairly stable. So if you were to rerun this multiple times, you'd probably get the same average and the same kind of upper and lower highest density intervals. I like 5,000. Don't know why. You can also run more. There's not a huge benefit to running more. Depends a lot on the speed of your machine. Although split half is much quicker at this point than it used to be, thanks to the RCPP package. Okay, let's run this. So we'll see over here that we've got our little timer running. I'll make this a wee bit bigger. This will run separately for each condition. It will give you a little message to say that the condition is complete. Depending on how big the data set is, depending on how many conditions, how many permutations, different parts of this might take a longer or shorter depending. So you may have noticed that there the transition between having completed the condition 1 and condition 2 was quite quick. We move on to actually calculating the estimates. If there's a lot of data, so at the minute we can see here that the sample size is 57 for each of these time points. I've run this with data sets with hundreds of people, and it's usually that bit that takes a little bit longer. But it's just worth bearing in mind that sometimes things can take longer. Okay, so the printed output is quite simple. I'll show you how to get more if we save the split half output into an object as well. So separately for each condition, each of our time points, we get the number of participants. I included this largely because it's a nice check just to very quickly make sure that there isn't something going wrong with a particular participant. If there's too few trials or something's going wrong, then it can be that participants end up being removed from this. Less so now that the code's been updated slightly. But it's always worth checking that this n matches the actual sample size that you're expecting. The main estimate is our Spim and Brown corrected correlation between the halves. So again, this is the average of our 5,000 splits. In this case, actually, it's not looking too bad. If this was a questionnaire, it'd be awful. I mean, it still doesn't make it any better that it's not a questionnaire in terms of actual psychometrics and its relation to the observable effect sizes and so on. But from what I've seen, from other people's data sets, from reported estimates from these kind of tasks, actually this is not looking too bad. So we also get the lower and the higher HDI bounds. So this is the 95 percentile upper and lower bounds. I think it's worthwhile reporting that HDI or CI, whichever terminology is useful for you, to give us more of an idea about the distribution of estimates. So it's one thing to have a point estimate, it's another thing to be able to say that our estimate is actually quite tight to that point. Largely this is dependent on the sample size. It's just important to note. Okay, so what we'll do just now is save our split half object into something that we'll just call it out1, just for ease. Now this is going to run in the same way. As I said earlier, based on the number of permutations, this is probably going to give us the same numbers. Okay. You'll note that there's a message to say var.trialnum is depreciated. It's not needed anymore. You don't need to specify it. It's just still in there so that it doesn't break people's code if it's not needed. Okay. So now that we have this out object, it is here. So I revamped this largely so that it can work with the split half.multiverse code, which I'll put into a different video when it's a little bit more stable. This is a little bit more hopefully mirroring what we would expect from other kind of statistical analyses tools. So in this case, our output has the call specifications so that we can track whether it was the different score, the conditions, and all of that kind of stuff, so that we actually have that information as well, which I think is useful. It has a copy of the data. This is purely so that, again, other functions can use it, or if you save the object, then kind of everything's there that's needed to recreate it. The estimates is a list of all of the reliability estimates that are calculated as part of this. So in this case, we ran 5,000 permutations across 2 conditions, so that's why we have our 10,000. Now this is largely so that we can look at the distributions. It's largely so that we can make the most of that aspect of it as well. We also have the final estimates. This is exactly what was printed earlier. The only addition is that in the console printing, I removed the split half 95% low and high intervals for the uncorrected estimates. So normally for split half reliability, because you have less trials to correlate, you would normally end up applying the Spearman Brown correction for attenuation, I believe. Spearman Brown correction in any case, which is why this 0.61 is a decent amount higher than the 0.45. So that would be a normal practice there. One final thing that that I've added fairly recently that is still has 1 or 2 minor bugs that I'll also explain briefly here, is the ability to actually plot within split half and to plot that distribution in rain cloud plots. So the main thing that we have to kind of sort out first, it doesn't like treating the condition list as numeric for reasons unknown to me. So we're just going to very, very quickly, again, there's going to be better ways of doing this, but we're just going to recode the time variable so that it's characters rather than numeric, and that just seems to help things work. So we know that 1 is 1. We're just going to call it 2 because we know that if it's not 1, it's 2. There isn't any missing stuff there. Okay, so let's, for ease, we'll just copy our previous call to split half, and we're just going to add plot equals true. Okay, now this is giving us so this is giving us an issue. One of the things that split half does in the initial stage is check through the variables specified that they exist in the data set, including the condition list and the compare list. So because we've changed that, we just need to change that back to 1 and 2. If anybody has any issues with split half, feel free to raise an issue on the GitHub page that I'll also put in the link. Split half's in fairly active development, and I'm always really keen to figure out how it can be better for people. So if anything is unclear or isn't working, do let me know, and I can try and fix it. If you want to help code things, feel free to to submit a pull request as well. Okay, so let's just expand this plot a little bit. So in the rain cloud plot, we have our estimates that we remember from earlier, so our 0.61 and our 0.50. The rain cloud is our distribution, which I think is quite nice. It gives us the density of the estimates. We also have our 95% HDIs here as well. And each of the individual points here is an individual one of the reliability estimates from the individual splits. Now I wanted to mention this briefly because I've seen other approaches where they may have taken only a single random split or only a few random splits to estimate reliability. And indeed that's how I did this early on. The problem with that being is that any individual split could be anywhere between, in this case, in excess of 0.8 reliability, as low as, let's say, 0.1, or in this case, almost zero. So it's important to have a large number of splits so that we actually have a much more robust estimate of the range of reliability estimates as well. In a future video, I'll cover the multiverse functionality within splithalf, the splithalf package. In that case, it allows you to run this same code across a large number of possible data processing specifications, for example, in outlier removal, typically, and trial removal and things like that. And it also then allows you to plot the reliability estimates and distributions across those different specifications, which I find is a really interesting approach to see the impact of something as fairly minor as, do I remove response times greater than 2000 versus 3000 milliseconds, and decisions like that. Which can have some quite large impacts on the reliability estimates that you observe. So thank you everybody for watching. As I say, the links, I'll put a load of links in the description. Feel free to reach out if anything's unclear, and if you have any suggestions for the package, let me know. Thanks everybody for watching.